A mind-bending event has taken the astronomy world by storm. A marathon gamma-ray burst that defies the rules and leaves experts scratching their heads. Just when you thought we had the cosmos figured out, nature delivers a cosmic puzzle. Could this be evidence that our current theories are missing something big? But here's where it gets controversial. This burst didn't just last longer than any other on record. It repeated. And it's shaking up decades of astrophysical assumptions. Typically, gamma-ray bursts, GRBs, are sorted into two simple categories: brief flashes that last less than 2 seconds, and longer events that end in a matter of minutes. But earlier this year, astronomers tracked a high-energy light show labeled GRB 25002b that roared to life not once, not twice, but 3 separate times over several hours. Even before the gamma rays blazed, soft X-rays flickered, hinting that something unusual was brewing. The oddity didn't stop there. This burst seemed to originate outside our galaxy, pointing to a phenomenal powerhouse far beyond the Milky Way. Leading the detective work were Antonio Martin Carrillo from University College Dublin and Andrew J. Levan of Radboud University. Their international teams pulled together the efforts of NASA's Fermi satellite, China's Einstein Probe, the world-class Very Large Telescope, and even the iconic Hubble Space Telescope. Each instrument contributed a critical clue, unveiling a signal that Martin Carrillo described as 100 to 1,000 times longer than most GRBs, and unlike anything seen in 50 years of observations. And this is the part most people miss. GRBs have always been viewed as one-off catastrophes, so a burst with repeat performances is almost heretical. But what's really behind GRB 25702b's weirdness? Normally, gamma-ray bursts strike once, exhausting all their energy in a single, cataclysmic shot. In this case, the Fermi satellite recorded 3 distinct energy surges, spaced by thousands of seconds, followed by earlier X-ray activity revealed by the Einstein Probe. The timing of these flashes wasn't random. The third surge arrived precisely when mathematicians would expect, based on the intervals between the first two. That hints at a repeating mechanism deep inside the source, rather than a standard, unrepeatable explosion. Strangely, the amount of gamma-ray energy from GRB 250702b isn't that different from other distant bursts. What's odd is the pattern. The classic formulas that relate the intensity and total power just don't stack up for each of these pulses. Most scientists would expect the afterglow, the fading light in X-ray, infrared, and radio, to align with a jet shooting from a compact object. And in some ways it does. Yet the infrared light was extremely red, suggesting a cloud of dust surrounding the cosmic drama. So where exactly did this cosmic enigma occur? For many, the obvious answer would be our own galaxy. But here's the twist. The Very Large Telescope pinpointed a fading, extremely red speck of light. Then, Hubble zoomed in and spotted a distant galaxy at the exact same location, suggesting the burst originated billions of light years away. To be seen from Earth, the explosion had to be staggeringly powerful. Spectroscopic observations confirmed heavy dust, and while the source is relatively near compared to many GRBs, it still sits firmly in extragalactic territory. Now comes the most debated part. What could possibly spawn a GRB with this profile? One theory, already sparking heated arguments, proposes that a black hole shredded a star that wandered too close. This scenario, called a jetted tidal disruption event, TDE, might explain the repetitive explosions. Examples like Swift J1644+57 have shown that magnetic fields around black holes can create erratic, stop-and-go jets. Alternatively, the researchers considered that a compact white dwarf star might be repeatedly grazing past an intermediate mass black hole, larger than normal black holes, but not quite galactic giants. Each close pass could rip away part of the star and feed the jet, producing bursts spaced by the star's orbital cycle. Could GRB 250702b fit the old model? where a huge star collapses in a one-and-done blaze of glory? It's not off the table. But it doesn't explain how you'd get several pulses separated by hours instead of just a quick, intense flash. Some wonder if a foreground galaxy could have split the light and duplicated the burst by gravitational lensing. But the varied shapes and colors of the pulses argue against that. Let's dive deeper into the light show. Unlike most GRBs, the first signals from GRB 250702b were soft X-rays, followed hours later by the brightest gamma-ray pulse. Usually, gamma rays arrive first and dominate. This flip-in sequence challenges established rules. Infrared light dimmed rapidly, while radio telescopes detected a faint source, consistent with the physics behind jet-powered explosions, but still not quite matching textbook patterns. One more controversial clue. The burst did not occur in the center of its galaxy. That's important, because disruption events fueled by supermassive black holes should happen in galactic cores. Instead, an intermediate mass black hole away from the heart of the galaxy makes more sense here. The red color? Most likely dust lanes that soak up blue wavelengths, not an uncommon feature in cosmic jets, but it beautifully matches the strong X-ray absorption seen. Astronomers also wonder, could a supernova be involved? In a classic tidal disruption case, X-ray signals vanish quickly after the jet shuts off, but radio waves can keep rising over months as the shock wave expands. Continued X-ray and radio monitoring will be key to understanding what happens next. If a supernova did play a role, it might reveal itself in infrared weeks after the event, although searching through layers of dust is tricky. Spectroscopic studies should also help clarify the distance to the burst and its environment. Pinpointing the exact redshift, how far away the source is, will reveal the true energy behind this record-shattering event. Lead scientist Martin Carrillo summed it up. We're still not certain what caused this. But our research marks a huge step forward in solving the mystery of this extremely unusual and thrilling object. Now, here's the big question for you. Are we looking at a brand new type of cosmic explosion, or is this just an extreme example of a process we already know? Could the established rules of GRBs be overdue for a rewrite, or will new data fit this event into the old playbook? Tell us where you stand. Do you think this mysterious burst is rewriting astronomy, or is there a conventional explanation waiting to be found? Drop your thoughts below and let's spark some debate.